going. Okay, so we have our dietary proteins. We have our pancreatic proteases that are going to convert these into amino acids. The amino acids are taken up by the intestinal enterocytes by simple diffusion, passive diffusion. Good, I'm hearing a resounding no. Well, how are they taken up?
Secondary active transport.
Yeah, secondary active transport by the amino acid transporters. And what are they using? Sodium, yeah. They're using that sodium gradient. So that was a brief review for what might be a final exam coming up in a little bit. So once these amino acids are in the circulation, they are now available for all tissues. And so all cells, of course, have amino acid transporters to be able to take these amino acids into their cytoplasm. Now, under these conditions, in the fed state, because we've just consumed a meal, so these are dietary proteins, we are in, again, an anabolic state. And so insulin signaling, this is something we didn't talk about. This is an anabolic state. Insulin has this global effect on the body to push everything into building. That's what anabolic state means. It's signaling all of the cells pretty much to say, you know, we've got food coming in from the outside. We are going to be in a high energy state and we're going to have building blocks. So this is the time to start our construction. So these amino acids are primarily going to be used for protein synthesis. So this is our protein synthesis machinery, and we're supplying it with a lot of amino acids. We're getting the signals going, so yeah, let's build protein. Now, if we have a lot of protein, a lot of amino acids in our diet, we only have a certain capacity of protein synthesis. So what happens to the rest of the amino acids that are not taken up by cells and they're not used for protein synthesis? Do we have a storage organ like adipose tissue? Nope. So we can't store them like a little pool of amino acids. Now, of course, we do have a pool of amino acids in our circulation at all times, but that's very small. So where do all these excess amino acids go after a meal? Excreted, right? So the point of this is that whatever we take as dietary source, we are going to use for protein synthesis, or we are going to excrete the rest of them. Okay? So what we're talking about today is nitrogen balance. So the nitrogen that comes in the form of amino acids is going to be assimilated. What is another source? What is another use for amino acids that come in through the circulation besides protein synthesis? What can amino acids be used for? Think nitrogen. Nitrogenous bases, right? Nucleic acids. So remember that each one of our purines and each one of our pyrimidines has two nitrogens in there. And the source of those nitrogens in building these bases is going to come primarily from amino acids. There are other nitrogen compounds, containing compounds, that we can make, and these also come from amino acids. Again, this is all anabolism. This is all the body building structures because we have all of these rich building blocks. Now, we don't have a store for them, so trying to use these for energy, you haven't seen anything mentioned here about using them for energy. Trying to use amino acids for energy is delicate because we don't have a store. Adipose tissue, yeah, we all got it. You know, we've all got plenty stores of fat. So when our glucose levels start to go down, we're going to rely on our secondary source with our fat tissue. We have a store so we can extract that fat, we can mobilize it, and we can use it. The same principle is going to happen with amino acids, but we don't have a little pool of amino acids, so we have to get these amino acids from our proteins. And this is where it becomes a little bit dangerous. So if we go into a fasting state, now, initial fasting state, where we're just coming out of a fed state, so we're in that postprandial state, that period of a couple few hours after we've eaten, where we're transitioning into a fasting state so that we have glucose available for energy by glycogenolysis, we're starting up gluconeogenesis. Do we really need to use amino acids at that time for energy? No. So the capitalizing on amino acids for energy source is not going to be very important at the beginning. Our glucose levels start to go down because our glycogen stores are emptying. So now let's talk about fasting at 24 hours and beyond. So we have enough glycogen in our liver to support our blood glucose level for 24 hours in a normal activity state. We're not talking about an exercising or a decathlon here. Just normal state. When this goes down at 24 hours, we are going to transition into fatty acid oxidation. So now remember, this is not a light switch. We don't go from using glucose to bang, ending glucose using fatty acids. This is that smooth transition because at the beginning of the fasting state, glucagon signaling is causing the release of fatty acids from adipose tissue. And so that adipose tissue will release the fatty acids, and early in the fasting state, liver will begin to metabolize fatty acids, so will skeletal muscle. The transition is smooth, but at 24 hours, our primary energy source is fatty acids. Okay? Can you see where that is a high yield step 1 question? This is the kind of question they ask. NBME does this too. You transition at 24 hours into a fast, what is your primary source of energy? The correct answer would be fatty acids. Now, as we start getting out to this point, what the body is doing is transitioning itself because its job is to protect us. We don't know when we're going to eat. Your metabolic system does not know. It's not connected with your thought thinking, well, I'm going to eat in 30 minutes. It doesn't know this. So what we're going to do now is we're going to start transitioning into amino acid catabolism. So now we're going to start taking our amino acids and we're going to start using those for energy. We don't have a pool. So where are we going to get the amino acids? From our proteins, right? So we're going to start capitalizing on our pool of proteins. And where is the largest source of proteins in our body? Skeletal muscle. And so there's an enormous amount of protein there. So we can afford to turn our proteins back into amino acids because we have so much skeletal muscle. Yes?
Does that start at around 24 hours?
No. Again, it's a smooth transition. Amino acid oxidation will actually occur at the beginning of the fasting state, but it's a very tiny amount. So the contribution of glucose at the beginning of fasting state is really high. Lipids at the beginning is less, but still there, and amino acids is very tiny. And so it's kind of, I call it like a slingshot effect. So as glucose is coming down, fatty acids coming up. As fatty acids are maximizing, now we're starting to get amino acids to prepare for when our fatty acid reserve disappears, okay? So picture individuals in, I mean, it's not a very pretty picture, but picture people that are political prisoners and they're on starvation diets. Picture the horrible prison conditions in most of our wars, where individuals, they all look like us when they first go in, and then all of a sudden, the next thing you see is they're very lean. They're okay, but they're lean. Well, what is that? They're burned through all their fat. They're down to maybe 1% body fat. Then they're still being given a little bit of bread and water every day, and then what happens? Now you've got skin hanging on a skeleton because they've transitioned into amino acid metabolism for energy. Okay.
So for board's purposes, is there a point in time at which this predominates over fatty acid oxidation?
Days.
Days?
Days, yes. So think of days to weeks.
Days to weeks. Okay.
Yeah. And again, it's all going to be dependent on the individual's metabolism, which you'll hear about in the last 2 weeks, is controlled primarily by the thyroid, pituitary axis, and also the adrenal glands. So depending on that activity, controlling metabolic rates and also physical activity. But when we're talking about this level, maximizing amino acid use in energy production, we are really talking about days to weeks. So that's why I say this is not normal. This is not normal. So an individual that's undergoing a religious fast, those are typically a day. That's fine. You know, they're going to probably have a little bit of juice, they'll have a little bit of glucose to support their metabolism. They're not going to have any problems with ketoacidosis. They're not going to have problems with muscle wasting. But think longer. Somebody's out on a deserted island for a week or two, and they're nibbling on a little bit of berries. That's not enough caloric intake, so they're going to have to start using their reserves. So how do we capitalize on extracting our proteins from our muscle to turn those back into amino acids? Well, remember that proteins all have a half-life. So remember what a half-life is. If we have time on the x-axis and we have protein amount of any specific protein, if we start measuring this amount of protein at time 0, we will be able to measure a certain amount of protein. With time, the amount of protein is going to go down if we follow, let's say, one of those protein in the pool. So let's say that we can take one protein, let's say an actin molecule, one protein of actin, and we can label that so we can follow the lifespan of this one protein. What's going to happen over time is that's going to disappear and eventually vanish. This is the lifetime of the protein. Every protein has its own lifetime. This lifetime can vary from seconds to days. And it depends on the protein. So you can imagine, if you needed to categorize protein longevity, proteins that are signaling proteins that have very precise regulatory function, you only want those around for seconds or minutes. So they're going to have a very short half-life, which means they're going to be synthesized and then degraded very quickly. What about proteins that can last for days or weeks? Structural proteins. So proteoglycans in the extracellular matrix, those can last for weeks before they're actually internalized, degraded, and replenished through biosynthesis. Okay? So now, let's say actin has a specific half-life. Let's say its half-life is 20 hours. So what we're measuring here, the half-life, is exactly 50% of the protein. Once we get to this point, This is the first half-life. Then we'll have this amount of protein, and so then we will measure the second half-life. And that will be 25% of the protein, et cetera, et cetera. So we can continue measuring these individual half-lives. So when we talk about a half-life of a protein, we're talking about the first half-life. When we have the maximal amount of protein that is measurable, and how long does it take to have only half of that amount of protein surviving? Now, when we're in a fasting starvation state and we've got to start extracting our proteins, 20 hours is an awful long time. What if this is actually 60 or 100 hours? And you really need these amino acids for generating energy. What we want to do is accelerate the pool of amino acids. So there's two ways of doing this. We can increase degradation of the protein. So we can increase the rate of protein loss by decreasing the half-life, or we can decrease biosynthesis of the protein. So remember, all proteins are turned over. They have their own half-life, and then through gene expression, we can restore the protein. So the way the body's going to do this is, instead of controlling degradation of proteins tends to be fairly consistent. There's not a lot of regulation and degradation of proteins, because remember, here we're talking about the proteasome. So the proteasome is that intracellular complex of many proteins that look like a barrel. And the way I look at it, that's called a trash can. And you put the protein in on one end, and out in the bottom comes amino acids. Okay? So degradation of proteins is pretty constitutive, unregulated. What about biosynthesis? So this will be another introduction to endocrinology. So cortisol is made by the adrenal complex, the adrenal gland. We saw epinephrine. So epinephrine and its partner, its neurotransmitter, norepinephrine, those are responsible for rapid metabolic changes. Rapid means you enter a fight or flight reaction and you need instantaneous response by your liver, by your muscle, by your adipose tissue, by your cardiac muscle, by your breathing. So those are fast metabolic reactions because of a certain situation that you need to take care of quickly. When we step up to cortisol, cortisol is more of a long-acting metabolic regulator. It's longer acting. And what this is responding to primarily is stress. What we're talking about here is the body undergoing a metabolic stress. So your energy levels, your overall energy levels are struggling, they're suffering. That is going to trigger cortisol release. And this is good stress. What the cortisol is going to do is it's going to block protein synthesis. So if we block protein synthesis, what is going to happen to our free amino acid pool? Increase.
What's the difference between biosynthesis of proteins and protein synthesis? Is there
Same thing.
Okay.
Right, same thing. Interchangeable.
Okay.
Biosynthesis is just, it's more of a big umbrella term. Protein synthesis is more correct for the specifics we're talking about.
Okay.
So what this is going to do is increase our amino acid pool by slowing protein synthesis. Now, cortisol is not going to stop it, but it's going to slow protein synthesis. We are going to rely on the half-life of proteins as they're being degraded to increase our pool of available amino acids. Okay? So now a little preview for endocrinology. We've got short-acting metabolic effectors with our catecholamines, like epinephrine. We've got longer-acting control of our metabolic reactions through cortisol. What sets the basic level of metabolism? Thyroid, yeah. And this is a good piece of information as we move into endocrine. Our T4 and T3 hormones that we'll be talking about, how those are synthesized, those are your really big control. So that is not control of metabolism in a short term or even in a medium long term. We're talking about the duration of somebody's life. Okay? So that's why hypo or hyperthyroidism is so dangerous. Because what you're doing is you're turning up global metabolism or turning it down for a very long duration. So somebody, the most common one is hypothyroidism, a low-acting thyroid. What happens to those individuals over a long period of time? What's the first thing you see?
Weight gain.
Weight gain, yeah. Because what you do is you're turning down the entire global physiological chemistry. And then over time, they start gaining weight. Okay, that is not something that is a clinical crisis that they're going to come to you to fix. What's the next thing they're going to start experiencing? Fatigue, tiredness. And that's why typically when somebody comes to you, first thing you're going to do is you're going to measure their weight, you're going to look at their chart and see if there's been weight fluctuation. That's a big indicator of metabolic problems. And then they're going to, you're going to see this, it's over like, boy, over the last year you've gained about 30 pounds. What's going on? I'm not sure, but boy, I sure have been feeling tired lately, right? My heart rate is kind of slow, my breathing is slow, I just feel like a slug. There you do a thyroid test. That's one of the first things, okay? Longer, medium acting is the cortisol. Monitor the protein pool here. And now once we have the proteins available to us, yes, I'm drawing a structure in front of your eyes. What is that? Glucose. It's an amino acid, and this represents one of the 20 side chains, right? So why did I draw this in front of you? Because it's very important when you're treating patients with protein disorders to remember the amino acid structure so you can draw this in front of them and impress them. Just kidding. They don't care, is right. So let's use an example here. Let's convert this to a real amino acid. Let's put a methyl group on there. Let's see who can win the bonus points. What amino acid is that? Okay, not glycine. Alanine. Alanine! Yay! Shoot. Alanine. So for your exam, you have to memorize all 20. No, just let that go forever. Remember that? Tar and feather, right. So amino acid, what we're going to do is we need to metabolize this, and we need to do the same type of energy extraction reactions that we did for glucose and lipids. And this is oxidation. Now, instead of having a separate energy production pathways for all of our amino acids, why don't we modify the amino acid a little bit and then put it into our normal metabolic pathways? Like glycolysis or TCA cycle. And that's what we're going to do. So some amino acids are going to be broken down and put into glycolysis. Some will be broken down and put directly in the TCA cycle. Now, in order to do that, we have to prepare this molecule. So the first thing we're going to do is we have to get rid of that nitrogen. Nitrogen is a waste product for us. It is absolutely useless for energy extraction. Now remember, when we're doing these oxidative reactions, what we're taking are the electrons associated with the hydrogens. We're doing this off of the carbons because nitrogen and oxygen are too electronegative. They're going to hang on to these hydrogens as tight as they can. So that means that we do not have any enzymes that can extract these hydrogens and electrons from this nitrogen. So we need to get rid of it. So the first thing we're going to do is perform what's called a transamination reaction. So a transamination reaction means simply that we're going to take this nitrogen off of this amino acid and we are going to place it onto another amino acid. We'll look at that mechanism in a second. But when we do that, this is what we're going to get. Let's see if somebody can show their mojo.
Acetoacetate.
You're close.
Acetoacetate.
This is going to be converted into acetyl-CoA. This is where I need to get my phone out and like YouTube you guys, because the wrinkling face is like, this is foul, right? This is foul. This is really bad.
It's just a carboxylic acid?
Nope. This is the carboxylic acid. Oh, you're going to kick yourselves.
We don't know anything.
Where's our biochem majors? I'm just kidding. We forgot. Ooh, forgot this. Yeah. That was erase that stuff from Osgood and Garber, right? Okay, so this is converting alanine into pyruvate. One step. What we've done is we've removed this nitrogen. We've replaced it with a ketone group. And I'll show you how this is done in a second. And we've made pyruvate in one biochemical step. Now that we've done this, what can we do with pyruvate?
A lot of things.
A lot of things. We're in the fasting state. So let's say we're in skeletal muscle. Yeah, we're going to make acetyl-CoA and boom, TCA cycle and ATP. So we just found a path that we can use amino acid alanine to generate energy. What if we're in the liver, in the fasting state? We're going to make pyruvate, right? Gluconeogenesis, right? Because in the liver, this will be converted to oxaloacetate by pyruvate carboxylase. This is liver fed state. So the muscle's using alanine to make pyruvate to make energy. The liver is taking pyruvate and making glucose. So the liver's not using the pyruvate for energy. So in the fasting state in the liver, what's the liver energy source? Fatty acid oxidation. Remember, fatty acid oxidation is what's controlling the switch into gluconeogenesis, because acetyl-CoA is an activator of pyruvate carboxylase, an inhibitor of PDH, And this is coming from beta oxidation of fatty acids. Okay, so that's a little bit of yesterday brought forward. So here's your amino acids in your skeletal muscle. What we want to do is we want to convert this to its respective alpha keto acid. And this is going to be removing that nitrogen. We've got to put that nitrogen on somebody. So we're going to do this. We're going to put this on alpha keto glutarate, and we are going to make glutamate. Okay? Now, we have an option here. Yeah, let's do this. This is awesome. I like this. Okay. I'm excited. This is completely new to me. I'm making this up as I go. Glutamate. Wait, what? So glutamate has two directions in muscle. What we need to do is we need to regenerate this so we can keep processing our amino acids. How we're going to do this is by converting those amine groups into pyruvate to make alanine. Alanine goes to the liver, and the liver will convert the alanine to pyruvate, and then the pyruvate will be used for gluconeogenesis. So this cycle here of alanine being generated from these transamination reactions, going to the liver taking this, making glucose and putting it back into the circulation, is called the alanine glucose cycle. Okay? Now this happens under early fasting conditions. Okay? Early fasting conditions mean that we're just processing some amino acids for energy use, and muscle is getting rid of that nitrogen waste product by letting go of alanine into the circulation. Now, what happens if cortisol levels go up because you're going out further in a fast, and now you have to process more amino acids? Process means get rid of more nitrogen. This process will continue in muscle, but it's insufficient to keep up with the needs of the muscle cell for the carbon backbone. So what we can do is we're going to take glutamate and we're going to make glutamine. And this enzyme is called glutamine synthase. Okay? So what is the purpose of this reaction?
Is it
Well,
synthase or synthetase?
interchangeable.
Okay.
General rule, synthetases are enzymes that require ATP and energy. Synthases are enzymes that do not require ATP.
So
That is the proper biochemical convention, but that's not followed in textbooks.
okay.
So I would be careful about that rule. It gets mixed up a lot by authors. So now, the purpose of this reaction, we have our alpha ketoglutarate originally acquiring one nitrogen. But remember that the end of the R chain of glutamate has a carboxylic acid on it. So we're going to take advantage of that, and we're going to add another nitrogen. So glutamine now has two nitrogens. Glutamine then gets put into the circulation. And of course, pretty much you can guess, the liver's going to take that up for us. Okay? So this is the processing of nitrogen in skeletal muscle to generate its energy.
question?
Yes.
Just putting the enzymes on the new figure.
Oh, up here?
Yeah.
Sure. So this one here is the amino acids, respective transaminase. This one here is going to be ALT. Okay?
And then the one, alanine to pyruvate.
Alanine to pyruvate, this one here, this is also ALT in
So
liver.
it goes both directions.
Yes, yes. All transamination reactions are fully reversible. Taken up by the liver, and it's going to be placed into the mitochondrial matrix. So it's going to be transported into the mitochondrial matrix, not the cytoplasm of the hepatocyte. So keep the thought of aspartate on the side for now. We'll get into that a little bit later. But glutamine is going to be processed here, and the first reaction we're going to perform is converting this into glutamine to glutamate. Now this enzyme is called glutaminase. And we are not doing a transamination reaction here. What we are releasing is an ammonium ion. The next step is by an enzyme called glutamate dehydrogenase. And we are going to make alpha-ketoglutarate, which of course can go into the TCA cycle and provide substrate for gluconeogenesis. But this is also not a transamination reaction. This is also going to release an ammonium ion. Now, it's these ammonium ions that are being released is why we're doing these reactions in the mitochondrial matrix. Ammonia is bad under all circumstances except if you're cleaning your shower. It's not a bad base for cleaning a shower. In our bodies, this is toxic under all conditions. So what we need to do with this reaction is we need to capture this ammonia. Remember how volatile this is from chemistry? This can pass membranes and diffuse through the body literally in seconds. So that means that the next step of this reaction has to trap this ammonia into a stable inert compound. So what we're going to do is we are going to combine the ammonia as soon as it's generated in this small little tiny matrix compartment. We're going to combine it with bicarb to make carbamoyl phosphate. This is now safe. The nitrogen has been trapped, and this is no longer a toxic compound.
Where's the phosphate in carbamoyl phosphate?
There's two ATPs being used here. And where's the bicarb coming from in the matrix of the mitochondria? It's coming from carbonic anhydrase dissolving into the mitochondrial matrix. And what's the precursor of this? CO2 and water. And where's the CO2 coming from? TCA cycle. This is happening in the liver mitochondria in a fasting state. The energy charge is enormously high because we have beta oxidation from fats coming in. So do we have sufficient amounts of CO2 to make sure that this enzyme, this step here, is rapid? Yes. Energy charge is really high, so we have a lot of CO2 possibilities building here from the TCA cycle. So those are combining to form carbamoyl phosphate. Okay? So this is the movement of nitrogen from amino acids in metabolically active tissue, primarily skeletal muscle. We need to move the nitrogen onto other carriers. Those carriers are transported to the liver. We're going to unload that nitrogen and we're going to build up our sink of aspartic acid, aspartate, and then the rest of it will come in through glutamine and we're going to release it as ammonia, and then we're going to trap it in carbamoyl phosphate. The enzyme that does this is called CSP1, or carbamoyl Here's a good example of your rule that usually is followed. This is a synthetase. Carbamoyl phosphate, synthetase. This is actually used, I believe, pretty much consistently, the synthesase there. Yeah.
So should it be CPS then? Carbamyl, yeah.
A little bit of dyslexia there. Okay, so the nitrogen movement, we've gotten ourselves to carbamoyl phosphate, and we've gotten ourselves to building up our aspartate concentration. The next step is the urea cycle, because the liver is responsible for ultimately getting rid of all nitrogen in the body. Okay?